Okay, so in last lecture we were discussing parallel transport, and we wrote down this parallel transport equation for a vector. It is in the lower uh, part of the screen, and as you can see that it involves the Riemann-Christoffel connection. Okay, whereas the parallel transport actually contains information which is contains an invariant information about the space time. In particular, it carries information about the curvature of space time, although the equation doesn't seem to have that curvature of space time explicitly uh, in the equation. Okay, so uh, so what we did was basically we considered the infinitesimal loop and tried to see how to evaluate the parallel transport of a vector, and we figured that this equation needs to be solved in a perturbative fashion, and we said that, like, we defined the vector to be some value v naught mu at a particular point, and and then we substituted that on uh, in the equation and computed, uh, kind of gave a perturbative answer to the differential part of the equation. So there was a dv by d lambda equals some gamma factor, and what one does is basically substitute v0 here and ask what is v mu by solving this. Okay, and then what we did was we solved that. We got a first correction around v0 mu. Then we take this and put it back into the equation, and of course you need to correct the Riemann-Christoffel connection also. Taylor expand it around a particular point, plug those two pieces up into the equation, and we get something which looks a bit messy, but you get this is a Taylor expansion of the Riemann-Christoffel connection. This is the solution to the uh, parallel transport equation to leading order uh, in the uh, in the expansion, and rather to first subleading order in the expansion, and then you kind of expand this and you find that this equation can actually be written in terms of Riemann tensor. Okay, and so you get an equation which looks like this. Okay, now of course what we could do is, and which is what we did, was that, like, you try to solve this equation, get a next correction to the solution, but we also said that, like, okay, we can always work in the local Lorentz frame in which gamma is equal to 0, and you can reduce this equation to a form which was something like this, that v mu at lambda equals epsilon minus v0 mu. Remember, lambda equals epsilon is the same point at which v0 mu is defined, because the small loop had a circumference of epsilon. So you just took it around and brought it back to the same point. And that gave you a term which is only dependent on the Riemann tensor. Okay. Now, of course, that is not necessary to do. In fact, I mean, you don't have to set gamma to 0. If you just step back a little, then you'll realize that this statement would just say that, like, if you take gamma on the left hand side, you would just put the path covariant derivative acting on v. Okay. So it is not really necessary to set this guy to 0. It's a covariant equation now finally, so you could have called it a path covariant derivative. But either way, the information that is relevant is the information uh, about the Riemann tensor, which is sitting out here. Uh, and of course, the expression for Riemann tensor that we wrote down was a little different, in the sense that we had terms which were del gamma minus gamma gamma piece, and of course what you really need is del of gamma minus del of gamma with rho sigma swapped, and similarly gamma gamma with rho sigma swapped, but it is not there in this expression. And I claim that this is just half the Riemann tensor, and that's why you put the factor of half out here. But you still need to establish that it is antisymmetric in rho and sigma, which is actually enforced by this integral. Okay, or if you go down, write it in a little symmetric fashion, it is like this: x minus x naught rho d by d tau x minus x naught sigma And now rho and sigma indices are antisymmetrized, because if you integrate by parts, there is a minus sign when the d by d tau is acting on x minus x not with a rho component. Okay, fine. So we then kind of did this exercise by studying a tiny loop of a rectangular loop of length L in one direction and length B in the other direction. And in this integral, we found that out of these individual pieces along this rectangle, only one of them contributes, and that is the second integral, whereas the first and uh, third integrals basically just vanish because x2 does not change, and the fourth integral vanishes because x1 is equal to 0. Okay, but nevertheless, this non-vanishing piece of this integral correctly captures the area of this rectangle. So what we find is that the quantity that is contributing to this integral is proportional to the area of the loop. Okay, so that is the answer that we got, a times b. So but remember, this a times b is multiplied by half times Riemann tensor. So if your loop is of non-zero size, then if you want to get a parallel transport vector to be same as the original vector, you would essentially need the Riemann tensor to vanish. Okay, so getting back original vector corresponds to the statement that the Riemann tensor should be 0. Okay, and that is a statement of the space being flat, because if all components of Riemann tensor are 0, then you should be able to find coordinate transformation which can bring the space to the Minkowski form. Okay, fine. If that is not the case, then of course the vector does not come back to itself, and there is a contribution from the curvature of space-time, and that is a non-trivial effect that you should be able to pick up. Okay, fine. So this is something we had done last time. So let's get back to the stuff that we want to do today. So what we want to do is to consider a charged particle in electromagnetic plus gravitational field. Okay. So now, so far we have been looking at equation where there is no electromagnetic field. So in the absence of electromagnetic field, the equation of motion for a charged particle would be just the same geodesic equation. So particle carries charge, but if there is no electric or magnetic field, then there is no way of knowing that the particle actually has a charge. So therefore, it is just only the gravitational effect. Okay, fine. If there is no gravitational field, then we know what is the equation. That is the Lorentz force equation, that the acceleration of the particle times mass is the force, Lorentz force formula, and that is related to the electromagnetic field times the velocity. Okay, fine. So if you want to ask a question that if both these fields are non-vanishing, what would you do? Okay, and of course the natural guess would be that you replace right hand side of the geodesic equation by the Lorentz force term. Okay, now of course you need to do some modifications because you are writing this equation in a curved space, so you replace eta alpha beta, which is the situation when the gravitational field is not there, by g alpha beta. But barring that, you would naturally generalize this equation to this form. Okay, fine. Now, okay, so let's try to determine the equations which basically give the fields sourced by a charged particle. Okay, so so to do that, let's first kind of look at the uh, equations satisfied by the electromagnetic field. So this is a small exercise which is something you must have done in classical electrodynamics itself, or in when you studied special relativity, but if not, just go through it once. So the Bianchi identity for the electromagnetic field strength gives you these two equations. The divergence of magnetic field is 0, and the curl of electric field is related to the time derivative of magnetic field. Whereas the equation of motion gives you two uh, other equations, the Maxwell equations. One is divergence of E is equal to the charge density, and the curl of B is related to the displacement current times the current density. Okay, so this is kind of straightforward. You may not even need to do any calculation, I suppose. Okay, so we could ask the question, what is the current density due to a charged particle? Okay, and so if you have multiple charged particles and if they carry different charges, which I have denoted as En, then every particle would be located at some specific space-time point. It has its own space-time trajectory given by x and t. Then rho is just sum of all these charges. Okay, each charge is supported at a particular on a particular trajectory. Okay, the corresponding current density would be written as the same kind of expression times the velocity of every particle. Okay, so this is the way the non-relativistic description would be, or rather, non-covariant description would be given. But one can give a covariant description of that. That means you can write down J alpha uh, by writing down a four-dimensional delta function, and you write down this quantity as dx and alpha by d lambda. Okay, so there's a jump from three-dimensional delta function to four-dimensional delta function in this process. So we can check how this would be related to the individual components. Okay, so what to do that, what we will do is we'll assume that the zeroth component of the coordinate x is a monotonic function of lambda. Okay, if you do that, then you can use the following thing, that you could decompose the four-dimensional delta function into the spatial delta function plus the temporal delta function. Okay, and if you are looking at the zeroth component of the current, the covariant current, then you just get dx0 by d lambda, and oh, I should have put n there. Okay, and now we can just implement this transformation by using this delta function identity. Okay, so if you use this delta function identity, you would find that, like, if you write down delta of some function, then you can write down that as 1 over the derivative of that function times the delta of the argument with respect to which the integral is being done. So in this case, the integral is being done with lambda. So you take derivative of this quantity with respect to lambda times delta of lambda, and that would kind of go away by using this lambda integration. But the quantity that you get is a derivative of x naught n with respect to lambda sitting in the denominator. Okay, so maybe I can remove this for the time being. So if you do that, then you get a quantity which is dxn by d lambda inverse. Okay, this is looking horrible, but I will correct it. Maybe a bigger bracket will help. Inverse times dxn by d lambda, which is the original term. So when you carry out this integration of the temporal delta function, you get this quantity which is inverse, which cancels this with this piece, and you get the charge density, which is En times delta cube, which is precisely the quantity that we had written down earlier. Okay, which is this. Okay, so with only the spatial delta function integrations. Okay, so of course one could do similar thing uh, with the spatial component of the currents and in that case you get dxi by d lambda, and you would write that in terms of it's the same typo because I copied it, I think. But now what you get is that the delta function corresponding to the x naught component still gives you dxn naught by d lambda inverse, and just by using chain rule you can write that in terms of dx I by dt, which are the velocity functions. Okay, and that kind of gives you back the original current density that we have written down. Okay, so upshot of this is that this covariant form of uh, the current is the same as the non-covariant pieces that we had written down earlier. Okay, fine. So here's a small exercise that you can do. You can show that the Maxwell's equations that we had written down some time ago, okay, would imply that the current that is sitting on the right hand side of the covariant equation is conserved. Okay, uh, kind of trivial. You can also show that the currents that we had written down just now, which is this is a spatial component of the current, and this is the charge density piece. So this current density uh, is in fact something which satisfies the continuity equation, namely del alpha of j alpha is 0 for this definition. Okay. Uh, so this is just a few line calculation, but it is instructive. It will be useful later. In fact, we will have similar equation for energy momentum tensor soon. Okay, and that also I have left as an exercise. But if you know this, then the energy momentum equation is roughly same length calculation and same argument essentially. Okay, fine. So what we want to do is to generalize the equations of electrodynamics to curved space-time. Okay, and to do that, we will have to covariantize the equations. Okay, so although you know this equation, I might as well kind of keep it on the screen for a moment. Okay, so this is the equation that we are looking at. Okay, and so all we are doing is covariantizing, replacing the etas by g's and partial derivatives by covariant derivatives, and this is how the expression would look like. Okay, the current that we have written down was a current in the flat space. In the curved space, you need to kind of correct that expression. It's not just the En times delta 4 with the lambda integral times dx by d lambda, but you also get this factor 1 over square root of minus determinant of g. Okay, and mm, so one of the exercises is to check that, you know, when you take the flat space limit of this current, you get the current that we just wrote down. Okay, namely the same expression without this root minus uh, det g sitting in the denominator. Okay, any
Sir,
question? Yes.
so when we covariantize, let's say we want to go from STR to GR,
Yeah.
so do we covariantize the equations of motion or the action? I mean, are the result of these two process convergent? I mean,
Yeah, they are identical actually.
oh, okay.
Okay, so uh, in fact, like, if you write down, say, actions, many times you don't even need to covariantize the derivatives. For example, if you write down a scalar theory action, then remember the scalar theory action is a partial derivative of a scalar squared kind of term. It continues to be the same action even in the curved space. Okay, what differs is the volume element. Excuse me. The volume element, excuse me, the volume element in the flat space was just integral d4x. Okay, volume element in the curved space is not cannot be just integral d4x. You need to write down square root determinant g factor multiplying the volume element, because under general coordinate transformation d4x is not invariant. Okay, whereas under Lorentz transformation d4x is. Okay, so so what you need to do is really replace the volume element by an invariant volume element. That is it for the scalar field theory. If you write down electrodynamics also, you don't need to convert ordinary derivative to covariant derivatives. All you need to do is to change the volume element uh, to uh, the corresponding invariant volume element. Of course, when you write down del mu phi, del mu phi, and you want to contract mu with nu, that contraction, of course, would require a metric. Okay, so you replace eta mu nu by g mu nu, and similarly for electrodynamics. But you don't need to do replace partial derivatives by covariant derivatives in the action. Okay, and that is because if you actually replace them by covariant derivatives, you will find that those covariant derivatives are same as partial derivatives, both in the case of scalar and the electrodynamics. Okay, but this is not generally true. For example, if you try to write down a similar thing for the Dirac equation, already to start with, the Dirac equation is a little complicated thing to kind of write in a curved space. But if you do that, it is not that you just continue to use the partial derivative and you get the equation written in the curved space. That's not what happens. So you need to kind of introduce new sets of variables so that you can write down quantities correctly. Okay. But as far as equations of motion are concerned, covariantizing is the best way of dealing with them. Okay.
Okay.
Okay. Fine. So fine. So let's look at this equation, which is a covariantized form, and so it has certain properties. It's the the equation, the left hand side of the equation transforms. Uh, Remember, it has only a gamma index sitting around. Everything else is covariant. It transforms like a covariant vector under general coordinate transformation. Okay, that is first thing. If you work in a locally inertial frame, that means the local Lorentz frame that you would want to define, then this equation would reduce to this equation. Okay, and we know that this equation is valid uh, in the flat space, and therefore it is valid in the locally inertial frame. So therefore left hand side of the covariantized equation actually is uh, equal to 0. Okay, now using these two facts, we can also say that this equation therefore should be satisfied in all coordinate frames, because the left hand side of this equation is a tensorial quantity. Well, it's a covariant vector, which is a kind of rank 1 tensor. Okay, and since in the local inertial frame it vanishes, and therefore it would vanish in all coordinate frames which are related to this by coordinate transformations. Okay, fine. So here's the exercise which I was talking about, that if you do start with this form, which is the covariant form that we had written down in flat space. Just a second. Okay, so you take this, and if you do a general coordinate transformation, okay, then you need to show that if you do a general coordinate transformation on that, you get this expression. Okay, so that is the exercise. It's quite instructive. This is quite similar to what we did with the free particle equation in flat space. We just said that m d2x by dt square is equal to 0, and then we did a kind of coordinate transformation. We replaced t by some parametric variable to start with, and then we said that, like, okay, if I do a arbitrary coordinate transformation, of course I know if I do a Lorentz transformation, the equation does not change its form, but I want to do a random transformation, and that is how we kind of indirectly arrived at the geodesic equation. Then of course we derived the geodesic equation starting from the action principle defined on the world line of the particle and so on. But this exercise is pretty much in the spirit of the way we got the first geodesic equation. Okay. Excuse me. Okay, so from this we can kind of draw some general principles, and the general principles of uh, kind of converting a given equation to a equation in the curved space is to follow these two steps. One is that the new equation that you would write down in curved space should be general coordinate invariant. Okay, so it's a kind of a overkill. I should really be saying that it should be general coordinate covariant. For example, the curved space form of the Maxwell equation is covariant. It's a covariant vector, this thing. So yeah, so maybe I should just have called it general coordinate covariant. Okay. And second condition that it should satisfy is that it should reduce to special relativistic form, like in case of Maxwell, it should reduce to this form in a locally inertial frame. Okay, fine. So this would correspond to the condition that the equation that we have written down should go over to this equation, which is same as this equation, of course. Okay, so in a local inertial frame. Fine. So general coordinate invariant or covariance is something which is quite trivial. Well, trivial in the sense it's an exercise, but you can check that it would work out. Okay, and that is a condition which is a must. Okay, so we should kind of try to distinguish these two when we kind of go ahead and try to look at these kind of generalizations of flat space equations to curved space equations. Okay, so here's a question: are these uh, guidelines sufficient to uniquely determine curved space generalization of the equation? Okay, so we looked at this and we basically wrote replace eta by g, replace partial derivative by covariant derivative, and we said that like okay, here's the equation. Okay, so therefore you could ask the reverse question that like okay, is that the kind of good enough reason, or is that the right way of covariantizing it? Okay, and the answer is kind of yes, provided we use both the conditions. Okay, that means we demand that the equation is general coordinate covariant, and we say that that in the local Lorentz frame, that whatever the covariantized equation that you have written down reduces to the flat space equation. In case of electrodynamics, it would be this equation. Okay, fine. So if you demand both, the answer is kind of unique. Okay, but you could say that like okay, I may want to kind of keep the first condition because general coordinate covariance is a good thing to have in a curved space time, but how about kind of relaxing the second condition? Okay, now of course if you relax the second condition, then you know we would not be respecting what is called Einstein's equivalence principle, which states that in a sufficiently small neighborhood, the laws of physics in curved space-time are the same as laws of physics in the special relativistic frame. Okay, or laws of physics in special relativity. That is a statement, right? So, which is different from the initial weak equivalence principle and stuff like that that we had written down, because this makes a specific reference to what are the laws of physics in special relativistic system. Okay, so if we say that like we want to relax the second condition as to demand that Einstein's equivalence principle, which later on I'll just call equivalence principle and not keep writing Einstein's equivalence principle, but that's what we are talking about. Okay, then we could write down in more general expressions. Okay, so suppose we don't say that it should kind of reduce to um, it, I mean, it should reduce to the flat space or special relativistic equation in the local Lorentz frame, then you could have written down an equation which is like this. Okay, so it's the same piece when it starts off, in this particular case, g alpha beta times d alpha, but it's not just f beta gamma, but some bunch of terms sitting around here, where r is a Ricci scalar and r alpha beta is a Ricci tensor. Okay, you could have written down something like this. Okay, I just wrote down a couple of terms. You could have written down like n number of other terms also. Okay, fine. So if the generalization of the flat space equation is this, okay, then one thing is guaranteed, namely if you take the flat space limit of this equation, you would reduce to this equation. Okay, which is the original equation that we started off with. Why? Because in the flat space the Riemann Ricci tensor vanishes and Ricci scalar also vanishes. So r is 0, r alpha beta is also 0. Okay, so if that is the case, then only term that matters is 1, and 1 times f alpha beta partial uh, covariant derivative goes to partial derivative, and you're back to this equation. Okay, but if you are in a local Lorentz frame, then the story is different. Okay, now if you are in the local Lorentz frame, then even if you can kind of uh, bring the physics uh, into local Minkowski like geometry, it still carries information about the curvature of space-time. Okay, so in other words, you can set g alpha beta equals eta alpha beta, you can set gamma equals 0, but you cannot set r alpha beta gamma delta equals 0. This is some exercise which we did earlier, that coordinate transformations have sufficient number of parameters. You have 16 parameters in fact, to set 10 of these quantities to set this 10 quantities to whatever values you want. Okay, you have 16 parameters. Then we said that like additional 6 were the Lorentz ones, we did not touch it alpha beta, it preserved it alpha beta. Then we had exactly 40 parameters to fix gamma to whatever value we wanted, and we could set them to 0. But here we have 100 parameters, but coordinate transformation had only 80 of them. So there were 20 parameters you just cannot set to 0 by doing any coordinate transformation. So in that sense, if this quantity is non-zero, there is no coordinate transformation which can kind of set it to 0. Okay. Uh, so that is the reason why uh, this quantity cannot be 0 unless the space is actually flat. Okay, fine. So therefore, local Lorentz frame does carry some information about the curvature of space-time. Okay, fine. So what does that mean? That would mean that if you have this new equation, so let me kind of flash that equation now. So if you look at this equation now, then you would go to the local Lorentz frame and just forget about what is the effect of gravity or curvature. Uh, I mean, you don't even try to track that information. You just track the trajectory of a charged particle in arbitrarily small region in the presence of some electromagnetic field. Okay, fine. So you are not even trying to figure out what is the curvature effect. But if you only do this much, okay, it will give you information about the curvature of space-time, simply because if this equation is of this form, if A and B are non-zero, or any one of the two are non-zero, you don't need both of them non-zero, in fact. Okay, uh, even in small region, if you follow the trajectory of the particle, compare that with what the flat space equation would be, and you would be able to determine what this R or R alpha beta would be. Okay, fine. But if Einstein's equivalence principle was true, then in the small enough region, you shouldn't be able to find any way of determining what is the curvature of space-time. It should really follow special relativistic equation, and therefore you shouldn't be able to determine what is the scalar curvature or the second rank tensor curvature of the space-time by just tracking the path of a charged particle in an electromagnetic field. Okay, so therefore, if you are going to stick to Einstein equivalence principle, then A and B better be 0. Okay, and if that is the case, then you get a unique generalization of flat space equations to the curved space equation, such that in the local Lorentz frame, it looks like a flat space equation. Okay, it takes the flat space equation form. Okay, any questions at this point?
Sir, I had a
Yeah.
different sort of a question.
Yes.
When you say something like a particle has an acceleration a,
Yeah.
like given by, let's say, in some coordinate system where
Yeah.
the metric is sort of spherical, the coordinate system is spherical.
Okay.
So you say that the particle has radial acceleration a,
Okay.
some a constant a,
Hmm.
and others not in other directions.
Okay.
So that is a frame dependent sort of a statement, right? That in the sense that you can only define it once and for all in one frame.
Exactly. Yeah.
So just by writing this statement, what does it mean? In the rest frame or something?
No, no, no. So this is written in one particular frame. For example, if you go to the Cartesian coordinate system, then the uh, x, y, z, all components of this would be non-zero, right? The acceleration
Yeah,
component.
yeah, that is fine.
Yeah.
But we can still determine it using a coordinate transform if we know the initial frame.
Exactly. Yes. Yes.
So when one says that the particle is accelerating with a, is it in its own rest frame where its velocity is zero?
No. No, no, no. If it is in its own race frame, then its acceleration is also zero, right?
No, particle still feels acceleration, right?
No, but in its own race frame, it feels nothing, right?
It's not acceleration due to gravity.
Yeah. Any acceleration, right? In its own frame, you wouldn't feel anything.
No, I mean, like in general, you cannot make acceleration to be zero in any frame.
No, no. See, if you are in the rest frame of the particle, then the acceleration would be zero. No?
Not really. I mean, we do feel. I mean, in the coincident moving frame, co-moving frame, whatever it's called.
Yeah.
If my temp like at that moment, at some moment, if my velocity is some v, in a frame moving along with me with that velocity, which is inertial,
Yeah.
in that frame, I will have some acceleration.
No, 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 because your frame and that frame are inertial frame with respect to each other, right? So there is no acceleration with respect to that frame.
Why? I mean, but then we won't be able to measure acceleration ever.
Well, in your own frame, you cannot measure acceleration anyway, right?
But we do, right? Like even apart from gravity, all other forces we can measure. Even in a lab.
Yeah, but when you do that, you are not trying to measure the acceleration of the particle itself in its own frame, right? You measure the acceleration of the particle in the, say, lab frame, right? Or in the observer's frame, or in the detector's frame, or something like that, right?
Yeah, but even for a particle starting from rest, we do say that the acceleration is something. At that t equals zero moment, both the particle is at rest and we are at rest. The lab is at rest.
That is right. Yeah, yeah,
And even then we say something like acceleration is positive or something.
that is true. Yeah, yeah, but
So I mean,
that still makes sense, right? That those are kind of initial conditions that the particle at time t is at rest has, that means it has zero velocity but non-zero acceleration. Could still make
but
sense.
at any time t, we can say a statement on acceleration because we are making a statement from an inertial frame, but about a particle which is not part of that frame.
That is
It is
right. Yeah,
moving with the same velocity at that instant, but it is accelerating.
that I agree. That you can of course make.
Yeah, so that is what
Yeah.
a co-moving frame is, right?
No, the co-moving frame. Okay, co-moving frame is a frame in which everything is inertial with respect to you. Okay,
Okay.
you are looking at a frame which is like, you have an accelerating particle in your frame, then that fellow has some acceleration, and therefore it is not in your co-moving frame, because as the time ticks in your frame, that particle's distance which with respect to your frame is not increasing linearly. It is going to increase depending upon whether the acceleration is constant or not constant.
So
Okay.
co-moving frames can themselves be accelerating.
No, co-moving frames are the ones. Yeah, co-moving frames can of course be accelerating. Yes, I mean, but the generally co-moving frames are the ones which are the frames which are freely falling. Okay.
Okay.
So with respect, so it's like in cosmology, for example, you typically study things in terms of co-moving frames. So those frames are just freely falling. They are not accelerating with respect to anything. There is some gravitational field in the bulk, and the frame just kind of drags along with it. Okay, that's what you mean by co-moving frame.
Okay.
Okay, so in that frame, with respect to that frame, some other set of co-moving frame could be accelerated. Okay, so all co-moving frames in curved geometry are not kind of inertial with respect to each other, because everybody has a different acceleration, right? So imagine that, like, you have a, I mean, like, uh, say, suppose you are looking at gravitational field generated by sun, okay, and you have a particle at a distance which is like a distance of Earth from the sun, whereas another particle which at the distance like Jupiter from the sun. So the local accelerations are different, right? And therefore the particle is just falling freely with respect to um, the sun's gravitational field. For example, Jupiter is freely falling, right? Because there is no additional force which is acting on it. Okay. But that acceleration that Jupiter experiences is locally the co-moving frame is different from what the Earth experiences. So therefore, the moving frames of Earth and Jupiter are not inertial with respect to each other. Okay, is that fine?
Okay.
So, but in a small local region, you take sufficiently small region, then two co-moving frames would be inertial frames with respect to each other. But that is the statement of Einstein's equivalence principle. Okay, that in small enough region, if you look at two frames which are co-moving, then they should be they should satisfy special relativity and therefore be inertial frames with respect to each other. Okay.
Yeah.
Okay. Any other question? Okay. If not, let's go ahead and ask a reverse question now. Okay. That suppose Einstein's equivalence principle is not strictly true. Okay. Uh, then we could ask a question that at what scale uh, we will be able to see deviation from Einstein's equivalence principle. Okay, uh, say you are looking at the space which has a small curvature, like in the neighborhood of Earth. The space is curved, but not curved enough. Uh, so, if some experimentalist wants to question various kinds of equivalence principles and wants to know which equivalence principle is likely to be true in the realistic theory of gravity, okay, uh, then the experiment has to be conducted in such a way that it would question every possible equivalence principle. So, for example, Einstein's equivalence principle, you could ask the question that if that is not satisfied, then I would write an equation which is like this. Okay, uh, you don't have to write down all kinds of terms. For example, for this argument, I'll set b to 0. Just I take 1 plus a times r. This thing. How do we? What should the experimentalists do to see any deviation from the original equation that we had written down, namely a is equal to 0 and b is equal to 0 equation? Okay. Okay. What is the scale of such corrections? Okay. Now, remember that the Ricci scalar and of course Ricci tensor, but since Ricci tensor is term is set to 0, Ricci scalar involves two derivatives of the metric. Okay, and of course various other contractions with respect to metric. Okay, but the metric itself is a dimensionless quantity, right? Because you write down d tau squared is equal to g alpha beta dx alpha dx beta, and the d tau squared has a unit of length squared, but that is taken care of by dx alpha dx beta. So g itself is dimensionless quantity. As a result, Ricci scalar has dimension 2 because it involves two derivatives. Okay. Now, if you have a dimension full quantity, then it's a kind of tricky thing to say that suppose the Ricci scalar is or the scalar curvature is of order 1. Okay, that is kind of a meaningless quantity because this quantity is of order 1 with respect to some other measuring unit. Okay, so with respect to some distance scale of kilometer or megaparsec or micrometer, whatever, you have to kind of use some scale with respect to which you want to define this quantity. Okay, so we could ask a question: what is a natural unit a theory of gravity would have, which you could use to determine the scale of Ricci scalar when we say Ricci scalar is of order 1. Okay. Now, first thing that we of course notice from say this equation is that suppose b is 0 and a is not equal to 0, then it is 1 plus a times r multiplied in f beta gamma. Since 1 is just a number, it is dimensionless quantity. If you check dimensions of all the quantities here, it will tell you that a has to have such dimension such that a times r is actually dimensionless. I just argued that R has dimension of length to the minus 2, and therefore A is a dimensionful quantity and it should have units of length squared. So although this quantity is dimensionless, A is just a parameter in the equation, and therefore you need to ask the question, what is the scale of curvature that is relevant and that is hopefully measurable in an experiment. Okay, so this brings us to what are called natural units and natural scales and stuff like that. And one of the things that you may have learned in other courses also, that you can use Newton's constant, speed of light, and the Planck's constant to replace the units of length, units of mass, and units of time by what are called Planck length, Planck mass, and Planck time. Okay, of which we really need Planck length right now, which corresponds to this particular formula. Okay, now you would say that, like, okay, we are doing classical theory, where is this h bar? Okay, but you don't really need to worry about it right now. You could just say that, like, uh, you could write down the Planck length in terms of G Newton. Am I making a mistake? Just give me a second. Okay, maybe you should check the dimensionality of the equation that I have written down. Because I thought, like, if I set h, yeah, it should be to the power half. Because if I set h bar and c to 1, then G Newton has a unit of length squared. So this should be to the power half. So just a second. Okay, so it'll correct soon, but uh, so what we find is that, like, the unit of length that you could define, which naturally occurs in a theory of gravity, is roughly square root of the Newton's constant in natural units in which you set h bar and c is equal to 1. Okay, but if you don't set them, then this is a kind of formula that you have. Okay, now this length scale is pretty small. It is like roughly of the order of 10 to the minus 33 meters or something like that. Okay, so you want to ask a question: what is the curvature when you say Ricci scale is of order 1? Then it is of order 1 with respect to this length scale. Okay, to put it a little differently, a times the Ricci scalar would be the Planck length squared times the Ricci scalar. Okay, which is a very small quantity, because, as I said, Planck length itself is 10 to the minus 33 meters. Planck length square would be something of the order of 10 to the minus 66 meters square. Okay, that is the kind of number which would be sitting around if the Ricci scalar was of order 1. Okay, now that is a pretty small effect, and it would be, you know, very difficult to set up an experiment with current capabilities to pick up factors of that kind. Okay, although I must say that, like, the LIGO experiment does pick up effects of the order of 10 to minus 29 meters or something. So this may not be too far away to be able to do this measurement. Remember, 10 to minus 29 meters with in a linear length factor. If you're looking at quantity which is meter square, LIGO would be able to do 10 to the minus 58. Okay, that is not very far. Okay, so but the thing is that, like, uh, having curvature of order 1 is not a great thing to have, in the sense of doing a very careful experiment to actually figure out whether the equation is this or whether the equation is only 1 and everything else is 0. Okay, quite tricky that way. Okay, fine. If you want to get good result, maybe you want to have R to be of the order of 10 to the 60. Then then it is still 6 orders of magnitude smaller, this thing, but okay, 6 orders of magnitude small quantities are easy to measure for us now. Okay, so fine. So curvatures which are small are clearly kind of hard to detect, and therefore, even if you want to ask this question, which of course we should, at least every experimentalist should continuously question this, whether Einstein equivalence principle is correct or not, by putting lower and lower bounds on deviations from that equivalence principle. But for all practical purposes, for doing any calculation, it won't be unreasonable to assume that Einstein's equivalence principle is true. Because if these factors are going to be 1 plus 10 to the minus 30 or 10 to the minus 60 or something, then you might as well say that, like, okay, I mean, I'm not doing the calculation to that accuracy anyway, right? Unless there is an experiment which is going to detect quantities to that level. But then, of course, in that case, you may have to write down large number of possible terms and check out which one would be relevant and to the appropriate experiment for that. Okay, fine. So therefore, what we will do is we will use the equivalence principle. By that I mean Einstein's equivalence principle, to generalize any equation that we have in flat space to the corresponding equation that we have in curved space. Okay, just appropriately covariantize, replace etas by g's, and write down the equation. Okay, as long as it has uniform transformation property with respect to Lorentz transformations, they would continue to have the same kind of transformation properties under general coordinate transformations. Okay, but clearly, as I said, that if you are talking to an experimentalist who wants to do like say fifth force experiment, or try to study deviations from Einstein's gravity, there are various proposals where gravity kind of becomes softer, kind of non-relativistic kind of behavior at very high energies. Any of such checks would of course require you to question this way of generalizing equations, uh, uh, and of course, yeah, each one of them will have some experimental consequences. If one has capabilities to measure such small effects, uh, it would tell us how to put bounds on various different equivalence principles. Yes, any
Sir,
question? Yes.
is this anyway related to this minimal coupling that we introduce in the action while deriving Einstein's equation?
Well, uh, two things. Yeah, we define the covariant derivative, right? That covariant derivative is the one which contains the minimal coupling effect, right?
Yes, sir.
Okay. Now, covariant derivative has been used for by demanding that when you take a derivative of a tensor, you get a tensor out of that. Okay, fine.
Yes, sir.
So as long as you write down a covariant derivative which does this, okay, and if you kind of you know don't respect any specific equivalence principle, then you could add terms to the covariant derivative, which would kind of allow you to write down the expression. Okay, for example, you could write down a term which is a tensor term which is added to the covariant derivative. Okay, remember the covariant derivative by itself is a tensor quantity. Okay, in the sense that, like, when it acts on something, it takes a tensor to a tensor. Okay, now if you take the covariant derivative and add a tensor to that, then covariant derivative acting on a tensor gives you tensor. Original covariant derivative acting on a tensor would give you a tensor, and a additional tensor multiplying the tensor on which the new covariant derivative is acting. That product of two tensors is also tensor, so the quantity would continue to be tensorial. Okay, now in pure gravity, it is hard to find a quantity which is a first rank tensor constructed out of metric. So all the tensors that we have constructed are second rank, fourth rank, or zeroth rank. Okay, so without adding something external to gravity, it is kind of hard to modify the covariant derivative notion in uh, maintaining covariance under general coordinate transformation, or maintaining the tensorial properties of the action of the covariant derivative. Okay, so that is the statement. Okay.
Okay.
Okay. Moving the wrong part. Yeah. Fine. So let's ask what happens to Klein-Gordon equation. Okay. So with Einstein's equivalence principle, you just replace the partial derivative by covariant derivative and eta alpha beta by g alpha beta. Okay. Now, of course, if you have studied this equation independently, you will realize that you don't need to do this much really. Okay, because the curved space Klein-Gordon equation contains G alpha beta D alpha, but this derivative can be just partial derivative. Okay, but since I'm using the rule that you replace partial derivatives by covariant derivatives and metrics by the metric eta by metric G, you can just convert this into this form. Okay, uh, if you try to actually check how d beta acts on phi, you will find that this covariant derivative acting on phi does not contain the connection, and in that sense it is still it is just a partial derivative. Okay, so this is just a formal way of writing, but in reality first derivative is partial and the second derivative is a covariant derivative. Okay, fine. Now this covariantization satisfies certain properties which guarantees that this equation is correct, and that is that initially the left hand side was a scalar, and the curved space equation also satisfies that condition that it continues to be a scalar. When you convert this to local inertial frame, then you can always set gamma to 0 in the local inertial frame, and this would reduce to the flat space equation. Okay, because in local inertial frame we have sufficient freedom to convert G to eta and set gamma to 0. Okay, so therefore these two statements tells you that if this flat space equation is valid, then tensorial property of this equation, namely that this is a rank 0 tensor, tells you that if it is valid in the local inertial frame, it is valid in all frames which are related to that by coordinate transformations. Okay. So
So
therefore,
shouldn't there be an m square? I mean, otherwise this is just the wave equation.
yeah, you could put m squared, but m squared is not playing any role. No? That is why I didn't write. Okay, because there is no tensorial quantity sitting around there. So you could write down m squared phi equals 0. That will just go as m squared phi equals 0 piece additional. Okay.
Yeah.
So I kept only this piece simply because this is the one which should change from flat space to curved space. But I could add that piece. Okay. Fine. Besides, we haven't found the massless scalar in the universe anyway, so no need to put it that way. Okay. So what we'll do now is, okay, so this is something you can do for other equations also. We have already done for the Maxwell's equations. This is the generalization for the scalar. A similar thing can be done for fermion, but it's a bit tricky using this curved space variables. It is useful to kind of write down a different set of variables to write down those equations. We will come to that at some later stage. Okay, it requires writing down a different formalism completely. Okay, but we'll do that. Okay, so let's kind of try to derive what's called the Einstein equation, and that is related to the fact that if you can convert Maxwell's equation from flat space to curved space, Klein-Gordon equation from flat space to curved space, you can ask the question, what happens to the laws of gravitation and equations of motion for gravity itself, which we had studied in quote unquote flat space, namely the Newton's law of gravitation. How do you generalize that to curved space time? Okay, that is the question that we would like to ask now. Okay. So in this case, the first hurdle that we encounter is that the equivalence principle of any kind is of no use. Okay, because most of the equivalence principles tell you that in the local frame you do not see any effect. Okay, and since we are going to stick to Einstein's equivalence principle, it will tell you that, like, okay, if you want to work in the local frame and deduce some result and generalize that to a curved space, in the local frame you just don't see effect of gravity. Okay, so therefore equivalence principle is kind of not a useful guiding principle, which was a good thing for, say, scalar or for electrodynamics, but not good for gravity. Okay, so so therefore, what we'll have to do, oh, this should have been frame. Okay. So, so what we need to do is to go about finding this equation in an indirect way. We will basically be trying to make a make a guess here, and then try to kind of check that this guess is consistent. Okay, fine. Okay, so one of the reason, of course, why we cannot do this is that unlike the electrodynamics and Klein-Gordon equation, there is actually no simple notion of an equation of motion for a metric in flat space time. Okay, that is one of the hurdles that we have. Okay, now of course we do have an equation of motion for gravity, but to relate gravity to space-time metric, which is what uh, Einstein's theory would tell you, uh, would tell would also mean that you should convert the Newton's equations into equations of motion for the metric. Okay, but the metric being constant in flat space time uh, has no guidance to give you when you want to convert that to Kraut space. Okay, so that is the reason why I was saying that we are going to make a guess which is based on what we learned in the electromagnetic theory, and we kind of generalize that uh, and implement the same kind of stuff for gravity. In a non-relativistic situation, these equation for the electromagnetism and for gravity seem to look the same. Okay, so we could at least say that, like, okay, that seems to be a encouraging kind of pointer, and we might as well see whether that pointer is going to be useful. Okay, so the equation of motion for electromagnetic theory is something like this. You know, some operator constructed out of the partial derivatives acting on the gauge field is equal to some source. Okay, we in fact know what this is. You know, this is just uh, in a specific choice of gauge. This is just the Laplacian acting on the gauge field, which is related to the current. Okay, that kind of equation one has. But if you try to kind of write down more general theory of electromagnetism, which involves higher derivative terms, you know, f to the 4 terms, or square 1 plus f squared to the half, some square root kind of terms, actions, you can choose whatever you want. Okay, they would still have a form of this kind, that there are a bunch of derivatives acting on the gauge field, which are equal to the source, the current. Okay, so we'll assume something similar for the metric also. So we'll say that, like, okay, you replace gauge field by metric. Okay, and there is some function of derivatives acting on the metric is related to the source. Okay, and we would like to kind of ask what kind of equation can we write down here uh, which satisfies certain consistency conditions. Okay, so for that, let's first try to figure out what kind of source that we could have on the right hand side of this equation. Okay, now we know that in the theory of gravity, it is the mass of the particle which is the source of gravitational field. Okay, so therefore you would want to kind of um, use a source which is constructed out of mass of the object which generates the gravitational field. Okay, fine. So what we want to do is that, you know, we would try to determine what the source is, but we will also want to kind of say that whatever equation we would get, okay, if you try to reduce it to a non-relativistic equation, it better produce the Newtonian equation. And Newton's equation was a Poisson equation, which is Laplacian acting on the gravitational potential is equal to rho, where rho is the mass density. Okay, it is this mass density which is responsible for producing this gravitational potential. Okay, fine. Now, the problem here is the following, that this is a non-relativistic equation, okay, where you write down the mass density on the right hand side, whatever is the mass distribution that anybody gives you, you can use that and try to solve for the gravitational potential. Okay, but in the relativistic dynamics, mass is not a conserved quantity. Okay, conserved quantity is energy. So what you would want to do is to replace the quantity here, which is mass density in the non-relativistic limit, by energy. Okay, that would be a probably more appropriate thing to do. Okay. Only problem is that energy itself is not a Lorentz scalar. Okay, so even if it's kind of a conserved quantity in the sense of uh, in the sense that, like, if you are looking at time independent configurations, then the energy of the total configuration would be conserved. Okay, but with respect to Lorentz transformations, energy itself is not a scalar. Okay, so what you would want to do is to write down a 4 vector. I have a equal to sign missing. Really bad. Okay. So, so what we would want to write down is a 4 vector p mu or p alpha, which is m times dx alpha by d lambda. Okay. So if you do that, then uh, then you could use this object, which is a 4 vector, and try to use p alpha in this equation, and try to write down the covariant form of the equation. Okay, but we have in fact know that p alpha itself is a component of the energy momentum density. So for a multi-particle system, we would be really writing it in this form. Okay, so and that is T alpha beta, with beta taking 0 value, is the momentum current, or momentum density rather. Okay, so what we really need here is we need to elevate rho from mass density to energy density to the the momentum 4 vector to the component of the energy momentum tensor. Okay, so if you do that, then what you would get is that you need to replace this rho on the right hand side of Newton's equation by a tensor which is called the energy momentum tensor, whose alpha 0 component is written out here, and its alpha I components are the components like this, where dx I by dt are the velocity vector, is a velocity vector of nth particle. Okay, so if you combine these two pieces, you actually end up getting T alpha beta, with alpha 0 components being these and alpha I components being that. Okay, so it's a covariant expression for this quantity. Okay, now by now you should know that if you have only one such term and a delta cube, if you convert delta 4, you would get 2 such quantities. This is what happened in the case uh, of electromagnetic current, for example. Okay, so so here's a piece where you write down this expression in a specific form. You get 2 pieces out here because you are kind of writing down the momenta explicitly, and what we want now is to write down T alpha beta on the right hand side of Newton's equation. Okay, and we want to ask a question: what is the quantity on the left hand side which would give you which should be equal to the energy momentum tensor? Now, of course, given the fact that the right hand side is an energy momentum tensor, you would want the left hand side also to be a tensor. Otherwise, under general coordinate transformations, 2 sides of the equation would transform differently. Okay, fine. So what should be the quantity on the left hand side? Well, that depends on various conditions. One of the conditions is something that we have already defined, namely that when you take the non-relativistic limit of a flat space and non-relativistic limit of this equation, you should be producing the Poisson equation for Newtonian gravity. Okay, so that is one condition that we have to impose on whatever equation that we would write down. Okay, fine. Now this T alpha beta, by virtue of having these 2 terms symmetric with respect to each other, is manifestly symmetric in alpha beta. So that is one result that we have. which tells you that the left hand side of that equation should be manifestly symmetric in alpha beta indices. Okay, so that is one condition, one additional condition that we have. Okay, fine. So here are a couple of exercises. One is that you check that the T alpha beta that we have written down here, okay, transforms like a second rank contravariant tensor under general coordinate transformation. Okay, that is one thing. And the second thing is that you can show that if you choose free particle energy momentum tensor, okay, then this energy momentum tensor is conserved. Okay, that means del alpha of T alpha beta in the Minkowski space is equal to 0. Okay, now as I was saying some time ago, that this result is related to the earlier result that I had asked you to check, namely you show that this current, no, not here, but that this current is conserved. Okay, yeah, that whatever current that we had written down earlier, which is right here, this form of the current, okay, you show that del alpha of J alpha is actually 0. Okay, whatever manipulation you need to do there is exactly the same manipulation that you will have to do here. Okay, so in that sense, if you do that exercise, this exercise is trivial. Okay, so I think I'll stop at this point. We will start building the left hand side of this equation, starting from the left hand side of the Newton's equation for gravity. Okay, so that we'll do in the next lecture. Any questions?
Sir, I have a question from last class.
Okay. So,
So,
do
yeah,
you
I
want me
can
to go to that
simply,
page?
no, I can just say,
Okay.
I mean,
Okay.
when we form that parallel transport, the
Yeah.
global one from
Yeah.
lambda naught to lambda,
Yeah.
you said we cannot simply integrate that equation to,
Yeah.
I mean, we have to formulate that in terms of P rather than
Yes.
V.
Yeah.
So why can't we do that? I mean,
Because all the quantities are functions of lambda, no?
yes.
So uh, you can't just move the quantity in the denominator and say log of this is equal to the other quantity. Okay, let's go back.